Welcome to section 2.2, the linear regression model. Of course, in the previous section, we considered ordinary least squares regression as little more than an algebraic tool, but in reality, OLS is much more than just a simple algebraic tool. Economists usually want to use their OLS estimates to make some sort of prediction, to see whether relationships are significant, whether our explanatory variable can adequately explain the dependent variable, or if it can be used to forecast values that might come about in the future. So they want to draw conclusions if one of the variables actually changes. Now, we will define, or Verbeek defines for us the statistical model using three different notation sets. What you'll notice as we go throughout the semester is that through the text, that Verbeek is going to alternate between these three notation sets. The first one, given by equation 2.24, is a familiar scalar-based mathematical notation. So here we have y sub I is a function of an intercept, beta sub 1, and then we have k explanatory variables. So we have x sub 2, x sub 3, and so forth up to x sub k. Then, if I can take these out of order, 2.26 is the full matrix notation. Right? So here we have y is equal to x beta plus epsilon. 2.25 is this kind of odd hybrid notation that Verbeek uses quite often. So what we're going to define is y sub I, which is a scalar, right? It's the ith observation of y, is equal to x sub I transpose times beta plus epsilon I. So x sub I transpose, what we're going to find out on the next slide when I expand this notation out, it's equal to a column vector, a row vector of the ith observations of the data set. Okay. So, Verbeek reminds us that you remember, I mentioned in the previous section that whenever we use Greek letters, those are unknown population variables. So these are relationships or numbers that exist in the population of all possible values, but as Greek letters, the Greek letters are used to remind us that these are parameters that are, although they're non-stochastic, right, they take on discrete values, those values are unknown to us, and they need to be estimated. So in these models, you'll notice we have two sets of Greek letters. We have the betas, those are the intercepts and the slopes, and then we have the epsilons. The epsilons are the stochastic disturbance terms. When we apply our OLS models, we receive estimates of these values. B is the Latin analog to the Greek beta, right? So B1, B2, up through B sub k are our OLS estimates of the true unknown population values, beta 1 through beta k, and E sub 1 through E sub n, which are our OLS residuals, can be thought of as our estimates for the true unknown disturbance terms, epsilon. Now, to expand upon this a little bit, I'm repeating for you 2.24, the scalar notation. That should be very familiar and comforting. And the next expression below it is Verbeek's hybrid notation, which was given by equation 2.25. So y sub I, which is the ith observation of the dependent variable y, can be expressed using matrix notation or vector notation here as x sub I transpose times beta. Beta is the column vector of the OLS parameters. Excuse me, not the OLS ones, the population parameters. The population intercept beta 1 and all the population slopes. And then x sub I transpose are the ith observations of all the explanatory variables. So we have 1, we have x sub I2. So what that means is in the X matrix, right? The matrix of all the explanatory variables, x sub I2 is the ith row of x and the second column. So, and then x sub I3 is the ith row and the third column. So, Verbeek denotes this as x sub I transpose as this column vector. Okay. And then reminding you of the application of the matrix notation that we defined last time. So whereas before we used the matrix of B's, the OLS estimates, now we have the vector of the betas, where the betas are the population, the true unknown population parameters. Okay. And then expanding out and showing you the equivalence, I have on this final line what you might think of as the typical definition of X, the matrix of explanatory variables. And then in the middle line, what I'm attempting to do here is show you the equivalence between Verbeek's hybrid notation and full-blown matrix notation in the bottom. So x sub 1 transpose is the row of all the observations of explanatory variables for the first observation. You can see that in the first row of the X matrix in the final line, and then so on and so forth. So look at those, think about them a little bit. I find it useful to remind myself from time to time of this notation set until it becomes familiar and more second nature to you. Now, in a proper statistics course, what we would talk about is if we have this population. So we have an infinitely large population where there's this relationship between the explanatory variables and the dependent variable. And then the way classical statisticians would describe this process is that we take a sample from the population. So in other words, we would draw values from this population, and God willing, our sample is it's a random draw. So in other words, each observation has an equal probability of being drawn. And once we have this random value, this value that's drawn from the population, there's two possible views that we can have on the stochastic disturbance, or the values of the x's. The first view, the more mathematically simple view, is that these draws of x, these x sub i's, are considered fixed and non-stochastic. And one way, so I know many of you, at least if you got your undergraduate degree at Baylor, you used Gujarati's textbook. And Gujarati describes this first view of the x's being assumed fixed in repeated sampling. Think about what would happen if we were conducting a laboratory experiment. What if we were trying to determine the efficacy of a pharmaceutical drug? So in this case, the x's would be the dosage that's applied to the petri dishes of the virus or the whatever it is that we're attempting to test. So in this case, the X's, the dosage of the drug that we're administering are considered fixed, and we have repeated draws on these fixed values of the samples. Since the value of, or the dosage of the drug that we're applying has been fixed and non-stochastic, what that means is, as we consider the statistical properties of the OLS estimator, the X's can be considered non-stochastic. They're fixed values. In the second alternate view, a new sample is new draws of both X and epsilon, so that each time a new set of observations are drawn, we have new values of both X and Y. In this case, the X's are no longer considered stochastic, and we're going to have to use a little stronger mathematical techniques to derive the statistical properties of the OLS estimator B. And we're going to consider this a couple weeks down the road, or a couple chapters down the road. We're going to be implementing probability limits. So we're going to consider the properties of the OLS estimator as the sample size goes to infinity. We can do that even when the X's are assumed to be stochastic. We're going to start off, or Verbeek is going to start off in his text, implementing the first view, assuming that the X's are fixed in repeated sampling, just for ease of mathematics. Okay. Now, we assume that the expected value of epsilon, which remember was the population stochastic disturbance term given the value of X. So notice X, the value of the explanatory variable, is given to us with a Latin script. So what that means then is that we know the value of the X with certainty. Epsilon is a Greek variable, meaning that it does exist, but we don't know its value. Right? So the expected value of the ith observation of the stochastic disturbance term, given we observe the ith observation of the explanatory variable, is assumed to be 0. Or if we wanted to use different words to explain this, Verbeek is assuming that the explanatory variables X are exogenous with respect to epsilon. Okay. So, in other words, the X's are determined outside the model. We have a model that determines epsilon. The X's are fixed with respect to that model. They're determined by another process. And as we consider the determination of epsilon, we assume the X's are fixed. Much like in the previous slide, we talked about the values being fixed, assumed fixed in repeated samplings in a laboratory setting. With this assumption, we can compute the expected value of Y sub I given X sub I. Y sub I, if I insert or substitute in its definition, Y sub I is assumed to be Xi transpose beta plus epsilon I. Remember, this was Verbeek's intermediate hybrid notation. So the expectation of a sum is equal to the sum of the expectations. So what this means then is, if I'm taking the expectation of Xi transpose beta plus epsilon, the expectation of that sum is equal to the sum of the expectation of the individual parts. Now, the expectation of Xi transpose beta conditional upon X is equal to Xi transpose beta because each of those values is non-stochastic. It doesn't have a statistical distribution. So the expected value of a scalar parameter that doesn't have a statistical distribution is the value of the parameter. It's like saying, what's the expected value of 50? The expected value of 50 is 50. The expected value of xi transpose beta is xi transpose beta, because xi transpose beta does not have a statistical distribution. However, epsilon does have a statistical distribution, but remember, we assumed the expectation of epsilon I given xi is equal to 0. Now, you recall from the previous section, from section 2.1, B, which was the OLS estimator, we had the slope, B2, which was equal to the sum of xi minus x bar times yi minus y bar over the sum of xi minus x bar quantity squared. Intuitively, this was the sample covariance of x and y divided by the sample variance of x in the denominator. Or we could express this in matrix notation as x prime x inverse x prime y. Notice that in either specification, B is a linear combination of random variables y. So the yi's are random variables, right, because they have the component epsilon. The x's are assumed to be non-stochastic constants. So what this means then is that the OLS estimators are weighted averages, in essence, of the y's. So if the y's have a statistical distribution and B is a linear combination of the y's, then that means that B also has a statistical distribution. And the distribution of B will depend upon the distribution of the data used to construct it, which is our draw y. Okay. Now, I want to jump up and down and scream at this point. I guess I had this beaten in me in graduate school by Jan Kometa. It is critical, important, to understand the difference between B and beta. Now, I've tried to talk about this so far by saying B is in Latin script. And remember, what that means is that B is an estimator. Beta is a Greek variable. Beta is a true unknown population parameter. We believe it exists. It does not have a statistical distribution, right? It takes on a discrete value with certainty. Beta is our statistical estimate, B is our statistical estimate of the true unknown population values beta. B is a vector of random variables, therefore it has a statistical distribution. Beta is a set of fixed unknown numbers characterizing the population model, to quote Verbeek. Okay. Section 2.3, small sample properties of the OLS estimator. Now, I wanted to review a few statistical concepts which I know are familiar to, at least I hope they're familiar to all of you. The first is the mean, or the central tendency, of a continuous stochastic variable y. So I have a dependent variable y. The mean of it is denoted by mu. So again, remember, we have a Greek letter, meaning that it's a true population parameter. It takes on some discrete value that is unknown to us. Mu, the mean, is the unconditional expectation of y. Okay? And the way that good proper statisticians would describe the expected value is we integrate y times its probability density function over the entire domain, or possible values that y can take on. So this expression, in essence, we're taking each possible value that the mean of y could take and weight it by its probability of occurrence. We do this over all possible values. If y is continuous, that means that y can take on an infinite number of values. This weighting is done through integration. So, and y is the probability density function of y. Okay. Now, the expectation of a sum, so if I have two stochastic variables, x and y, and I want to find the expectation of the sum, I already gave this platitude a little bit earlier in this lecture. The expectation of a sum is equal to the sum of the expectations. So to operationalize that, the expected value of x plus y is equal to the expected value of x plus the expected value of y. The other result that we can implement regarding means is if y is a stochastic variable and let a be a non-stochastic constant. So that would be a number like 15. So the expectation of 15 times y is equal to 15 times the expectation of y. So what this means then is that non-stochastic constants can be factored out of an expectation operator. The expectation of ay is equal to a times the expectation of y. To review variance, again, if we were pretending to be proper statisticians, what we would say is the variance is described by statisticians as the second central moment. So a central moment, meaning we are subtracting the mean or the first moment from the computation. The variance is a measurement of dispersion. So the variance of y, what we do is, again, we take each, so we integrate over all possible values that y can take from negative infinity to infinity, and for each value we take y minus its mean or central tendency and square it and weight it by its probability of occurrence over the entire domain of y. What this gives us then is, in essence, the expected value of the deviation from the mean. It's literally what it is. It's a measurement of the dispersion of y. Okay. So the variance of a non-stochastic constant a times y is equal to a squared times the variance of y. And I'm not going to prove that because I think I'm going to give that to you as a homework assignment. It's very straightforward. Okay. Now, a very famous early result from ordinary least squares theory is due to Gauss and Markov. Carl Friedrich Gauss was this mathematician from who lived in the 1700s, and I guess I have to tell you a little tacky story. Do you remember the formula for the sum of the first n integers? So if I take the sum of 1 plus 2 plus 3 plus 4 plus 5 up to 10, let's say, that the sum from 1 to 10 is equal to 10 times 11 divided by 2. Or in general, we could say the sum of the first n integers is equal to n times n plus 1 over 2. So this result was derived by Carl Friedrich Gauss when he was in 3rd grade. So the story goes, according to my very entertaining Austrian math professor when I was an undergrad, that little Carl Friedrich was being very naughty in class. And his teacher, as a punishment, told him to go into the corner and add the first I think it was 200 numbers, right? So the sum of the integers 1 through 200. And little Carl Friedrich came back with the answer in under 2 minutes. And the teacher thought that he had cheated or had somehow memorized the result. And then he showed his teacher how it was that he derived this result. It was n times n plus 1 over 2. So clearly, Carl Friedrich Gauss was a mathematical prodigy. And some of the major results we have about the properties of OLS are due to Gauss. So these are the what Verbeek calls the Gauss-Markov conditions. You could think of them as the ideal conditions. So these would be the conditions where everything is right in the world. I like to describe it as the conditions when your data is clean and pure as the wind-driven snow. So the Gauss-Markov conditions, condition 1, A1, is that the expected value of the stochastic disturbance term is 0 for all observations of the data set. Okay. The second condition is that the epsilons, the stochastic disturbance terms, and all of the values of the explanatory variable are independent. So that means that each epsilon is unaffected by all realizations of x throughout the sample. Okay. The variance of epsilon I is equal to sigma squared for all values, or for all observations of the data set. In words, we describe this as homoscedasticity. Right? So the stochastic disturbance term has the same variance for all observations. The covariance of all stochastic disturbance terms is 0. So what this means is that even though epsilon is a Greek letter, meaning that it's unknown to us, we don't know what its value is, but if by some amazing circumstance we knew what the value of epsilon I was, it gives us no useful information for determining what the value or the properties of epsilon j is. So there's no variance between any two observations of the data set. Now we can describe these conditions in matrix form more compactly. Right? So conditions 1, 3, or assumptions 1, 3, and 4 can be re-expressed in matrix notation by the following expression. The column vector of the epsilons, it's a column vector, so it has n rows in one column. It has a statistical distribution with a mean of a column vector of 0 and a variance-covariance matrix that's given by sigma squared times I sub n. What that means then is that the variance of each observation is given in the diagonal term of this matrix. So we can take the variance of each individual element of the data set, and each covariance is equal to 0. The covariance is represented by the off-diagonal elements. So expression 2.29 much more compactly expresses the assumptions that we've made upon the model, upon the statistical properties of epsilon. Assumption A2, which was regarding the conditional expectation of epsilon. So that's the mean and variance of epsilon conditional upon the value of x. So A2 deals with the conditional expectation. 2.29 deals with the unconditional expectation, and they're the same, right? You see that. Okay. Now, the properties of the OLS estimator. The first one is that the OLS estimator B is unbiased. What it means literally to be unbiased is that the expected value of B is beta. So in other words, the central tendency is beta. We're not estimating beta with any systematic bias. Okay? So to show this, we'll do first a little bit of algebraic manipulation on B, and then we'll take expectations. So if I start with my matrix definition of B, which was x prime x inverse x prime y, and I'm going to substitute in the definition of y. Y is equal to x beta plus epsilon. And now if I break that rightmost parentheses, I get this expression on the third line, x prime x inverse x prime x beta plus x prime x inverse x prime epsilon. You'll notice that x prime x inverse x prime x, what I'm doing is I'm taking x prime x and pre-multiplying it by its inverse. So that means this becomes the identity matrix, and I receive beta plus this extra term. And this is how a lot of the proofs are going to go in this class. What we're going to do is we're going to start with the algebraic result beta, and through a little bit of manipulation I've shown, B. Starting with B, I show that B, the OLS estimator, is equal to beta, the true unknown value, plus this leftover or junk term. So here the junk term or leftover term is x prime x inverse x prime epsilon. Now if I take the expectation of beta, you remember the expectation of a sum is equal to the sum of the expectations. Beta is unknown to us, but it does not have a statistical distribution, right? It takes on some discrete value with certainty, but we just don't know what that value is, right? So what I can say then is the expectation of beta is equal to the the expected value of B is equal to the expectation of this sum, right? Beta plus the junk term. Now, the expectation of beta, since beta is non-stochastic, the expectation of beta is beta. And then x's, the x's, remember, we assume are non-stochastic in repeated sampling. We made that somewhat heroic assumption to make the math a little bit easier. So what this means then is I can move the non-stochastic x's outside the expectation operator. So the expected value of B is equal to beta plus x prime x inverse x prime times the expectation of epsilon. But you will remember that by assumption A1, the expected value of the epsilons is a column vector of zeros, meaning that the expectation of B is beta, meaning that B is unbiased. The OLS estimator is unbiased. To get the variance of B, the math stat definition of the variance is it's the expected value of B minus its expected value squared. And this is the matrix math analog to that. So it's a quadratic built around the deviation of beta, the deviation of B from its expected value beta. Now, if I take in the first result that the expected value of B is beta, this expression simplifies to the expectation of B minus beta times B minus beta transpose. B minus beta is equal to basically the junk term that we derived from the previous slide. And that was equal to x prime x inverse x prime epsilon. So I can substitute that into this definition and I get this expression. Now again, because the x's are assumed to be non-stochastic in repeated sampling, the x's can be moved outside the expectation operator. So I can do that to both the left and to the right, and I get this expression in the center, expectation of epsilon, epsilon transpose. You remember that from the matrix expression of the Gauss-Markov assumptions, this is equal to sigma squared times I sub n. So sigma squared is a scalar parameter that can be factored out, and I sub n is the identity matrix. So that can be simplified into this next expression. And now you'll notice there's one more simplification that I can do. So I have sigma squared x prime x inverse x prime x. So x prime x pre-multiplied by its inverse, you remember, becomes the identity matrix. So this can simplify to the variance of B is sigma squared times x prime x quantity inverse. Okay. The Gauss-Markov theorem. So this is the fantastic results. Given the Gauss-Markov conditions A1 through A4, the OLS estimator B is the best linear unbiased estimator, or blue. And if we want to express this a little more verbosely, we could say that among the class of unbiased linear estimators, so the estimator has to be a linear combination of the y's, and it must also be unbiased. So among the class of unbiased linear estimators, the OLS estimator has the minimum possible variance. Now, this is actually quite important. Notice we're not saying it has the smallest variance of all unbiased linear estimators that have been discovered. What the Gauss-Markov theorem is stating is that OLS has the smallest possible variance. In other words, a unbiased linear estimator with a smaller variance than OLS cannot exist. That's what Gauss-Markov is saying. Okay? So, to prove it, we will consider an alternate linear estimator. So a linear estimator is some linear transformation of the y's. So consider an alternate linear estimator A, and A has some intercepts, right? Some constant values, lowercase m, and then it has this set of weights with uppercase m, and those are weights that we apply to the values y. Okay. So if we take first the expected value of A and just treat this as an algebraic exercise, the expected value of A is going to be equal to m. Remember, these are non-stochastic constants, so the expectation of the lowercase m's, the intercepts, are the intercepts themselves, and then the cap m's are a weight or a matrix of non-stochastic weights. So that can come out. So I can say then that the expectation of A is equal to lowercase m plus uppercase m times the expectation of y. Putting in, so substituting the definition of y to get the second row, and then breaking that rightmost parentheses, I have lowercase m plus uppercase mx beta plus uppercase m times the expectation of epsilon. But we remember that by assumption the expectation of the epsilons are 0. So what we're left with then is lowercase m plus uppercase m x beta. Now, if my new cosmic alternate linear estimator A is going to be unbiased, the expectation of A must be equal to beta. So for the expectation of A to be equal to beta, the lowercase m's all have to be equal to 0, and mx must equal the identity matrix. Okay? And I claim that that's true by inspection. these conditions are fulfilled for the OLS estimator, just as a sideshow. So there is no lowercase m in the OLS estimator, and uppercase M for the OLS estimator is x prime x inverse x prime. So x prime x inverse x prime multiplied by x gives me that expression, x prime x inverse x prime x, which is the identity matrix. So these conditions are fulfilled for the OLS estimator. Now, without loss of generality, we assume that there's no intercept, so the lowercase m were equal to 0, and assume that the uppercase m, the weights that I apply to my vector of the dependent variable y, is equal to the OLS weights plus this other matrix of weights D. So I've re-expressed A, my alternate OLS estimator, as the OLS estimator plus D, where D is an n by k matrix. So to apply the results from the previous slide, for my new A to be unbiased, what has to happen then is that this new weight times x must equal the identity matrix. So we know that x prime x inverse x prime x is equal to 0. What this implies then is that the identity matrix is equal to the identity matrix plus d times x. The implication then I have at the very bottom, A is unbiased if and only if D times X is equal to a matrix of zeros. Okay. So that does put restrictions on this. Okay. Now, if I consider the variance of my new estimator A, I can derive the variance as I derive the variance using matrix math for the OLS estimator. So so going from the first line to the second line, I place in my junk term, right? A minus beta is equal to x prime x inverse x prime epsilon plus d times epsilon. And then as I multiply out all those terms, let's see, we get to the fourth line. That was just through algebraic manipulation. But you remember from the previous slide, what we found is that for A to be unbiased, x times d, or d times x, had to be equal to a matrix of zeros. So what this implies then is that if I look at the fourth line, the second additive term and the third additive term both must be 0 because dx is equal to a matrix of zeros. And I get this simplified expression. The variance of A is equal to sigma squared times x prime x inverse plus d prime. Now, to choose D to minimize this variance of A subject to the condition of being unbiased, what I do is I take matrix differentiation of the variance of A with respect to D, and it's equal to 2 sigma squared times D transpose must be equal to a n by k matrix of zeros. This final condition can be fulfilled if and only if each element of D is 0. So what this implies then is that the OLS estimator, excuse me, the linear unbiased estimator A that has the minimum possible variance is the OLS estimator. Okay, QED. Now, you should remember this result from the prerequisite course. An unbiased estimator of sigma squared, of course, sigma is a Greek letter, so our estimator of sigma squared, which is the variance of epsilon, is given by the Latin analog s squared. S squared is equal to 1 over n minus k times E transpose E. And just to remind you, E, remember, is the vector of the OLS residuals, so E transpose is a row vector of the residuals. So this is now equivalent to the third line, 1 over n minus k, times the sum of each of the residuals squared. Now, I should point out to you, of course you can see it, that the unbiased estimator uses n minus k in the denominator instead of the sample size n. The reason why is that there are only n minus k linearly independent estimates of epsilon sub I. So the E sub i's, which remember are the OLS estimates of the true unknown epsilons, they are constructed using the OLS estimators B1 through B sub k. Because of that, it means that only n minus k of the column vector of E's are linearly independent. Now, there's a much careful statistical proof of this using the trace of matrices. It's in this wonderful book that I have. It's this itty-bitty thin green text that's about half an inch thick with the very terse and foreboding title of Econometrics. So you can come to my text. We use this in the advanced econometric theory field course. So in section 1.4, you can see the proof of this. So anyway, the estimated variance of B. So you'll notice that the estimated variance, well, the true variance of B was sigma squared times x prime x inverse. Our estimated variance of B, we substitute s squared for the true unknown value sigma squared. And we get this variance covariance matrix. So the diagonal elements represent the variance of each of the individual OLS parameters. The off-diagonal elements represent the covariances between the OLS slopes and the intercept. Okay. Now, all the results that we've derived up to this point have we've assumed only that the epsilon have mean zero, are homoscedastic and independent, but we did not assume any parametric distributional form, right? We didn't say how they were distributed, just that they had some sort of statistical distribution with mean zero, homoscedastic, and being independent. If we want exact statistical inference in small samples, we have to assume a parametric distribution for epsilon. The typical assumption that's made is that the epsilons are normally distributed. So if the epsilons, if each individual epsilon is assumed to be normally and independently distributed with mean zero and variance sigma squared. So what that means is all the covariances are zero. The mean of each epsilon is zero and they're homoscedastic. If that is true, The B's now are a linear combination of the epsilons, which are now assumed to be normal, independent, and identically distributed. Then it's very straightforward to show that B, the OLS estimators, since they are a weighted average of normally distributed random variables, B now itself is normally distributed, since it is a weighted average of normally distributed random variables. Therefore, under this new assumption of normal disturbance terms, B is distributed normally with mean beta and variance sigma squared x prime x quantity inverse.